Thus far, as we've been working on systems of differential equations, all of the equations have been homogeneous, which begs the question then, how do we solve non-homogeneous systems? And really, the process with non-homogeneous systems is going to be exactly the same as the idea of non-homogeneous higher-order differential equations we saw before. In the past, we found out that x was equal to x complement plus x particular. And so we're going to do the exact same setup that we did before, this time just in matrix notation, representing the entire system. So for example, if I had x prime is equal to -1, 4, 2, 1 times x plus -8, 3. We would start by solving the homogeneous version by first finding x complement, taking a look at the coefficient matrix, and finding the eigenvalues. -1 minus lambda, 4, 2, and 1 minus lambda. That determinant is equal to -1 minus lambda times 1 minus lambda minus 8 equals 0. Multiplying it out, we get lambda squared plus lambda minus lambda is 0. And then finally a -1 minus 8 gives us -9 equals 0. And so we can see it factors to lambda minus 3 times lambda plus 3. In other words, our eigenvalues are lambda equals plus or minus 3. Taking a look then at an eigenvalue of 3, we plug into our lambdas the 3 to get -1 minus 3 is -4, 4, 2, and 1 minus 3 is -2, times our eigenvector k1, k2 needs to equal the 0 matrix. So -4 k1 plus 4 k2 equals 0, and 2 k1 minus 2 k2 equals 0. And really, both of these are pretty much the same. So if I add 4k1 to both sides, we get 4k2 equals 4k1. And divide both sides by 4, and k2 equals k1, which is really nice. Gives us a nice eigenvector of 1, 1. Then we go back and solve for the other eigenvalue of -3. Plugging those into our lambdas, we end up with -1 minus a -3 is 2, 4. And 2, 1 minus a -3 is 4, times the eigenvector k1, k2 is equal to the 0 matrix, which gives us 2k1 plus 4k2 equals 0. And the second equation is identical. So we'll subtract 4k2 from both sides to get 2k1 equals -4k2. Divide by 2, and k2 equals -2. Oops, sorry, k1 equals -2k2. So if we let k2 equal 1, then k1 would be -2. So our second eigenvector is -2, 1. Which means when we put it all together, we end up with our x complement is equal to c1 times the eigenvector 1, 1 times e to the 3t, our eigenvalue, plus c2 times the eigenvector -2, 1, e to the eigenvalue -3t. And then we just need to guess the form of x particular so that we can plug it into our equation and solve for the coefficients of x particular. Well, it looks like we've got constants added to our function. So with much the same strategy that we had before, we're going to assume x particular is a constant. We'll call it a1, a2. And if that's the case, then x particular prime is going to be 0, 0, the derivatives of constants. And so when we plug it into our original function, we end up with x prime, which is 0, 0, is equal to our coefficients of -1, 4, 2, 1, times x, which is our a1, a2, plus the -8, 3. So now we can go about solving this system for our constants. Multiplying through, we end up with 0 equals -a1 plus 4a2 minus an 8. And the second row gives us 0 equals 2a1 plus a2 plus 3. We can solve this system several ways. Let's multiply the top equation by 2. That'll give us 0 equals -2a1 plus 8a2 minus 16. And so when we add together, we get 0 equals 9a2 minus 13. So a2 is going to be 13 over 9. Plugging back into one of our original equations, then, we have 0 equals -a1 plus 4 times a2, which gives us 52 over 9, minus 8. I'm going to add the a1 to both sides, and 8 is equal to, getting a common denominator of 9, 72 ninths. So 52 minus 72 gives us 20, -20 ninths for our a1. This then tells us that our x particular is equal to a1, which is -20 over 9, a2, which is 13 over 9. Put it together then in matrix form, our solution is x equals x complement c1, 1, 1, e to the 3t, plus c2, -2, 1, e to the -3t, plus x particular, which is -20 over 9, 13 over 9. Or if we wanted to write it back in terms of our x and our y's, the x of t is equal to c1 times 1 e to the 3t minus 2 c2 e to the -3t minus 20 over 9. And the y of t would be c1 e to the 3t plus c2 e to the -3t plus 13 over 9. And depending on the format the problem wanted for our solution, we have now solved our system of equations. Let's try and solve one more example, just so that we can practice guessing the form of the particular solution. Let's try x prime is equal to 6, 1, 4, 3 times our x vector, plus, this time we're going to say 6t and -10t plus 4. Which, by the way, that last vector could have been written as 6 -10 times t plus 0, 4. You could see it either direction. Sometimes we see it term-wise organized by a similar coefficient. Either way, the process, the idea is still the same. First, we have to find the homogeneous solution, which we find by finding the eigenvalues of the coefficient matrix. 6 minus lambda, 1, 4, and 3 minus lambda, which is equal to 6 minus lambda times 3 minus lambda minus 4. Multiplying that out, we get lambda squared. Minus 3 minus 6 is minus 9 lambda. Plus 18 minus 4 is plus 14, and we know that has to equal 0. And so we can factor to lambda minus 7, lambda minus 2, and so lambda, our eigenvalues, are 7 and 2. Finding our eigenvectors then, starting with the 7, plugging the 7 in for our lambdas. 6 minus 7 is -1, 1, 4, and 3 minus 7 is -4. Times the eigenvector, k1, k2, has to equal 0. So negative k1 plus k2 equals 0. And 4k1 minus 4k2 has to equal 0 as well. Well, the first equation is easier to work with. By adding k1 to both sides, we find out k1 equals k2, which gives us that nice eigenvector of 1, 1. When we plug the 2 in, eigenvalue of 2, plugging it into lambda, gives us 6 minus 2 is 4. 1, 4, and 3 minus 2 is 1, times our k1, k2 needs to equal the 0 vector. So we have 4k1 plus k2 equals 0, and the second equation is identical. So we solve quickly by subtracting 4k1 from both sides to get k2 equals negative 4k1. Which means if k1 equals 1, k2 would be negative 4, giving us eigenvector 1, negative 4. And x complement solution, that is equal to c1, 1, 1, e to the 7t, plus c2, 1, negative 4, e to the 2t. This time we're going to have to do a little bit more work, though, to get x particular. X particular, because we have t's, and then we want to count down every exponent, we're going to assume it's going to be of the form a1 times t plus b1, and then a2 times t plus b2, which means x particular prime, the derivative of those expressions, are a1, a2. And so when we plug it into our equation, we find out x prime is a1, a2 is equal to our coefficient matrix 6, 1, 4, 3 times our particular solution a1t plus b1, a2t plus b2, plus the 6t and negative 10t plus 4. And so this is what we're going to have to play with in order to find what a1, a2, b1, and b2 are. Multiplying this out, we get a1 is equal to 6 times the a1t plus b1 plus 1 times the a2t plus b2 plus the 6t. In the second row, a2 is equal to 4 times a1t plus b1 plus 3 times a2t plus b2 minus 10t plus 4. And similar to what we did with our undetermined coefficients method, we're going to start to organize our terms to create a system of equations. First, we're going to look at an equation for the t's. From the first equation, there are 0 t's on the left. When I distribute, we'll get 6 a1t's. We'll get an a2t. And we'll get a 6t. In the second equation, we've got a 4a1, actually 0 on the left, then 4 a1s on the t's, 3 a2s on the t's, and negative 10 t's. We also are going to have a system of equations for the constants. I'm looking at the constants. The first equation is a1 equals 6b1 plus a b2 plus 0, and then an a2, which is equal to 4b1 plus 3b2 plus a constant of 4. And notice this gives us 4 equations and 4 unknowns, a system of equations that we can use to solve. Looks like it's going to be easiest to solve the first set of equations first. And to do that, I'm going to multiply by -3. And when I do that, the first equation is going to become 0 equals -18a1 minus 3a2 minus 18. The second equation, 0 equals 4a1 plus 3a2 minus 10. And when we add those together, 0 equals -14a1 minus 28. And adding 28 and dividing by -14, we get a1 is equal to -2. We then can solve for our a2 by plugging it into either equation. I'm just going to plug it into the second equation. We have 0 equals 4 times a1. 4 times -2 is -8, plus 3a2 minus 10. Add 18 divided by 3, a2 is equal to 6. Now, looking at the other equation trying to solve, we know a1 is equal to -2, and we know a2 is equal to 6. So I'll go ahead and plug those in. Then I will go in and multiply the first equation by -3. That's going to give us a positive 6 equals -18b1 minus 3b2. And so when I add together, I get 12 equals -14b1 plus 4. And so if I subtract 4 from both sides, I get 8 divided by -14 gives me -4/7 when I reduce. And just plugging that into my first equation here, we've got -2 equals 6 times b1, which is -24/7, plus b2. So if I add 24 to both sides, gives me 10/7, I believe. Yep. And so we put it all together, and we now know the form of our x particular. X particular is equal to a1, which was -2t, plus b1, which is -4/7, a2, which was 6t, plus b2, which is 10/7. And so we can put that all together to get the general form of x. X is equal to x complement, c1, 1, 1, e to the 7t, plus c2, 1, -4, e to the 2t, plus x particular, which is -2t, minus 4/7, and 6t, plus 10/7. Of course, we can write that equation, that solution, several ways. We could break up the x particular into its component vectors, which would give us c1, 1, 1, e to the 7t, plus c2, 1, -4, e to the 2t, plus the coefficients of -2, 6 times t, plus the constant vector -4/7, 10/7. And so that would be the same solution split up into its component vectors. Or if we wanted to express the solution as actually the equations of x and y, remember x comes from the first row, which would be c1 e to the 7t plus c2 e to the 2t minus 2t minus 4/7. And our y of t function would be c1 e to the 7t minus 4c2 e to the 2t plus 6t plus 10/7. So we have 3 different ways to express this final solution. Just for the sake of practicing to set up our x particular solution, I want to do one more example. And we're just going to set up the form of x particular because I think we're familiar enough with the process by now. Let's say we have dx dt is equal to 5x plus 3y minus 2 e to the -t plus 1. And dy dt equals -x plus y plus e to the negative t minus 5t plus 7. Well, if we were to write this in matrix form, it would be x prime, the coefficients 5, 3, negative 1, 1, times our x vector. The non-homogeneous part then would be our last vector, which would be negative 2 e to the negative t plus 1, and e to the negative t minus 5t plus 7. Of course, I could have written that non-homogeneous part in its components. If I did it that way, we would have x prime 5, 3, negative 1, 1 times x plus the coefficients of e to the negative t would be negative 2, 1, e to the negative t, plus the coefficients of t would be 0 and 5 times t, plus the constant vector 1, 7. And seeing those pieces can really help me figure out the form of x particular. We can see that we're going to need some a1, a2 coefficient of e to the negative t. We can see we're going to need some b1, b2 as the coefficients of t. And we're going to need some constants, c1 and c2. And that kind of covers all the pieces and possibilities. We could combine them to a single x particular vector, a1 e to the negative t plus b1 t plus c1, a2 e to the negative t plus b2 times t plus c2. And then we'd be able to go back and plug in to try and figure out what a1, b1, c1, a2, b2, and c2 actually equal. But we're very familiar with that process, so now I think the best use of your time is to go back and practice these on your own. Good luck on the assignment.